So I'm gonna talk about regularization and robustness in reinforcement learning. Are you familiar with reinforcement learning settings? Okay, so I'm just gonna introduce you to what it's about. In short, I would say that it's the art of making the right decisions. So, for example, consider the first decision that has ever been made according to the Bible. So you have Adam and Eve that are told to not eat from the tree of life. And according to whether they obey or not, the next situation will be different. Either they will get eternal life or they're gonna die, but will be able to distinguish between good and evil. So we could model this as Adam and Eve in a current situation S. They, according to what they do, to which action they take, they get some reward of eating or not the apple or whatever fruit it is. If they obey, they get eternal life, and if they eat, on the other hand, next situation of Adam and Eve will be to be mortal, to die, but on the other hand, to be able to distinguish between the yin and the yang. Historically, the first time reinforcement learning problem has been formalized was in the 19th century by Arthur Kelly, who was a British mathematician, well known rather in the field of algebra. So the problem he describes in his writings is, suppose you have a box. It is opaque. We don't see what's inside. So, and there are three types of amounts that you could get, but you don't know which amount they are, and you don't see inside. And at each step, you have the choice whether to take out some billet or a ticket, or to stop the game. So and this is one example of a reinforcement learning problem, because you sequentially take new decisions and get whatever rewards. So in this situation, the reward you're gonna get is the terminal one, meaning that the last ticket that you pick will be the amount of money that you will get. So the question is, when should you stop or continue picking tickets in order to maximize your expected return? And in fact, you can imagine a rainbow of applications where this kind of problem applies. Whatever applications such as communication networks, autonomous driving, healthcare, whatever. So you can think of it as a rainbow of applications. So now I'm going to introduce the setting. You have a discrete set of decision epochs from 0 to possibly infinity, which corresponds to the times at which you make new decisions and take new actions. You have a finite set of states and actions. So the states corresponds to where the agent is at some steps t, and A, the action space, is the whatever action the agent's gonna take. The transition kernel corresponds to where the agent will be brought at each step. So it's a mapping from state and action pairs to a probability over the state space. And we take a deterministic reward, R, which is a mapping from state action pairs to the real set, real numbers. And this corresponds to the immediate reward the agent gets from being in state S and having taken action A. And the optimizing variable is a policy. So a policy is in fact a sequence of decisions, of decision maps. So these decision rules map the state ST to a probability over the actions. And the objective that we want to maximize is the return. So this is our objective function. If you think of it as an optimization problem, this is the objective function that we want to maximize over this variable pi, which is the sequence of decision rules that you take. So this the notation is a bit heavy because I'm going to introduce another setting. So this dependence in P and R corresponds to the dependence in the Markov decision process model. P is the transition, R is the reward. This is the initial state action, and this corresponds to the expected sum of discounted returns. So this gamma T here, this gamma is the discount factor, which enables this to converge, actually, this sum to be well defined. And the value function is just the expectation with respect to the actions that you take. So you can either take this or that as an objective function. So and you can relate them through the expectation. And in this setting, as I said, we fix P and R, but in fact we don't know these elements. We don't know what is the transitions that you evolve in. You don't know what is the reward function that effectively models your income. So you could estimate it according to samples, but you will have estimation errors by essence. And the fact that it's dynamic makes it very sensitive to model estimation error. So an additional drawback of regular MDPs, Markov decision process in short, is that imagine you have an adversary that changes your environment suddenly at whatever step, then if you consider your model PR to be fixed, then your performance will drop significantly. So it's oblivious to adversarial dynamics, and one solution that addresses all of those challenges at once is the robust MDP setting, where the idea is quite simple, actually. It's you consider the model to lie in a specific set of models, and instead of maximizing your return, you're going to maximize your worst case return, meaning maximize your return under the worst model from that set of PRs. So formally, you have a robust MDP is an MDP where PR, the transition and reward, lie in a given uncertainty set. And you can think of this set as a confidence interval. So if you have an estimation of your P and R, you can take U as being the confidence interval that you have, and compute the worst case into that step. The optimizing variable doesn't change. You still want to consider the policies. And the objective this time is to maximize your return, but under the worst value function over the set of models. So before that, we only had this VPR, VPI PR, and now we have an infimum over all possible models. Any questions until now? And a big shortcoming that as I spend the most time, I think, during my PhD, is that in robust MDP, it is computationally expensive to actually solve this infimum that I showed you. So instead of standard dynamic programming, here you need to solve robust dynamic programming. So it's sequential robust optimization problems. If your set is a general convex set, it can take polynomial time. And imagine an algorithm that takes polynomial time at each Bellman recursion, so it can take a lot of time in the end. So So we wanted to address this using regularization. Now the question is, okay, what kind of regularization are you going to use? So in statistical learning, for example, in SVM or regression, whatever, we often add a penalty to the objective function in order to robustify the problem. So in that sense, like we wanted to use the same idea, but in a sequential framework. And the question is, what is the regularization that you're going to use in this sequential decision-making problem? So there were empirical works that did use regularization in reinforcement learning to improve policy exploration, improve stability during training. It's also computationally efficient because it doesn't cost much to add some additional term in your loss. But on the other hand, none of these regularization methods encompassed model uncertainty. So what we knew as regularized reinforcement learning before that was not always robust to model uncertainty. And I'll explain later on, I'll explain why it's not effectively robust, at least in the sense that we defined before. And on the other hand, we have the robust RL setting that does encompass model uncertainty, but is computationally expensive, as I said right before. So robust RL is much more expensive than regularized RL.
I have a question. So here, when you mentioned that it doesn't the regularized RL setting doesn't encompass model uncertainty, does this mean that if the true model is not known, the P and R are not known, if I use a regularizer and I solve this RL problem, I will not be protecting against those scenarios at all? Like
exactly. So I'll define formally what I mean by this. Okay. So you're advancing by some slides, but if you do regularization, at least when you do policy regularization with entropy, policy entropy, and things like that, what you do is in fact being robust with respect to the reward only. And I'll explain this formally later on. Okay, so these are the main contributions of that work. So when you do policy regularization, essentially you're solving a robust MDP, but with uncertain reward only, but not uncertain transition. So you don't encompass, in that sense, transition uncertainty. As an ad hoc result, we also derived the policy gradient theorem for reward robust MDPs using this regularization. And what we show, this is the main contribution, is that robust MDP is equivalent to regularization, where you have both policy and value regularization, meaning that your function regularizer depends on the policy, but also on the value function. And this leads us to like dynamic programming, a regularized version of it that avoids the minimization of robust MDPs. Which we call twice regularized Derman operators because of this double regularization, policy and value regularization. And in fact, the nice properties of these Bellman operators enable to do planning in these R2 MDPs. So modified policy iteration converges geometrically. And also one of the purposes of having a computationally efficient, robust method is also to scale it to deep setting. So this leads us to a R2DQN version of the DeepQ network that enables scalable, robust learning in continuous environments. So this is actually the timeline that we're going to follow in the rest of this talk. And first, I introduced some background on the Markov decision process. I actually introduced already the MDP setting. R is in red, just to make it clear. P is the transition in green, and you have an initial state distribution mu0 that we assume to be strictly positive. I didn't write it here. And policy, which we assume this time to be stationary. Instead of having the sequence of decision rules, we just take a stationary policy to make it easier. And actually, it doesn't lose generality. So so in case you're concerned. So the standard value function in a regular MDP setting is a fixed point of a linear Bellman operator, which is defined as this part of the equality, R pi plus gamma p pi v. And the regularized version of it, which is what we do in policy regularization, is in fact shows that the regularized value function, sorry, is the fixed point of this regularized version of the Bellman operator. So instead of having R pi plus gamma p pi v, we have a transformed reward, omega pi, R pi minus omega pi, where omega pi is whatever convex function. You can think of it as a KL or entropy, whatever. And in the robust setting, on the other hand, we have the robust value function to being a fixed point of this nonlinear Bellman operator. So here, this time we have a minimum over the uncertainty set of R pi plus gamma p pi v. And the question is, how can we have something of the taste of the regularized RL framework? So instead of having this minimum, can we add something here in order to avoid this minimization? So that's the idea. So just to recall the two facts, on the one hand, we have the regularized framework that doesn't account to model uncertainty. On the other hand, we have the robust setting that does account to it for it, but is much more expensive. So we want to take the best of both worlds. And we leverage some previous result of Yenga, which is one of the first papers on robust MDPs that shows that the robust value function for a given policy pi is the optimal solution of this robust optimization problem. So this is the inner product between the initial state distribution and the variable v. It's in fact the value function, subject to v being smaller than the robust Bellman operator. And what we can show is that, in fact, if you solve the robust feasibility constraint here, you end up with a support function, sigma r, that can be expressed as the well-known regularizers in deep setting that are used. So I'll explain this further later on. But basically, the idea here in this optimization problem is to solve the robust feasibility constraint, and we end up this with this regularizer. So the assumption is that the uncertainty set U is centered around a nominal model, and if you have only reward uncertainty, then you get this regularizer. So this P naught R naught can be thought of as the model estimation that you have on your model, and the uncertainty is only on the reward. So in that case, we have this regularized. Here you really identify the regularized Bellman operator that we saw before with the R pi minus omega pi.
So what is the P0, R0 stand for?
It's a nominal. It's like the center of, you can think of it as your model estimate. You have an estimate, but you have some error on it. So only for the reward. This is the assumption of that theorem. So this, you can think of it as a confidence interval for the reward, but you only have uncertainty on the reward. Actually, if we consider well-known methods that use regularization, at least in deep settings, like negative Shannon, KL, or Thales, we could rewrite all of these as rewrite them as an uncertainty set because of this relationship between the support function and the regularizer. So, for example, here you have the uncertainty interval corresponding to the negative Shannon, the one with for the KL, and etc. And in all of these cases, the transition uncertainty doesn't exist, meaning that you assume that your transition is fixed and known.
So here, you can only define for a particular regularizer class, or can you say that it, for any uncertainty set, I can find the regularizer with this theorem?
I would say it's a general result. So you could, whatever regularizer you can think of, if you have a correspondence with the support function, you can do whatever set from the reward. You can derive whatever set.
So how is the uncertainty divided?
So just it's very simple math actually, because here you rewrite the support function, and you want to end up with whatever regularizer you want to end up with this. So you find the uncertainty set that that achieves the maximum in the support function. There is a tricky part here, but I'm not gonna get into it. It's the dependence on pi in the reward uncertainty set, but I'm not gonna get into it, because actually in policy regularization you end up with stochastic optimal policies, but not deterministic, and in that sense, this doesn't contradict it because of this dependence in pi. Now, what if we generalize this to general robust MDPs, meaning with both transition and reward uncertainty? So this time we have uncertainty here in the transition and the reward. And then we can show that again, if we use the exact same method of solving the robust feasibility constraints, we end up with an additional term here in the regularization, which corresponds to the support function of PS, which is the uncertainty set at state S, evaluated at minus gamma V times pi. And the difficulty here, the challenge here, is the dependence of the regularizer on the value function. So in policy regularization, it's easy because once you fix your policy, you fix also your regularizer. But here, because of the dependence of V, which is also the optimizing variable, you have like a interdependence of quantities. But in any case, if we think of even more particular cases of these and take both uncertainty sets, so you can take whatever norm here, but just for a notation conciseness, it's L2 norm. You can find the support functions in a closed form. So, and end up with this regularizer. So the first term here, norm of pi s times alpha SR, is the support function for the reward set. And the second term here is the support function for the transition. And this defines our R2 Bellman operator. So if we take this as a regularizer, we can actually define those operator, the evaluation version of it, which is just the standard operator at the nominal minus the regularizer, and the optimal version of it, which is just taking the greedy policy into this evaluation. And we can show that it admits a unique fixed point under MILA assumptions. So I'm also not gonna get into the assumptions that we need. Okay, no, I'm not gonna get into it. So here we have the first term, omega-1, which is exactly this first part in the overall regularization, and omega-2 that depends both on pi and v, which corresponds to the second term in the overall regularizer. So this is contracting, it admits a unique fixed point, and we can derive, since it is contracting, we can derive a value iteration, policy iteration, and modified policy iteration, like any standard planning algorithm. And we can run them and compare the time computing time with the robust version of it. So in this table, we have a policy evaluation and 2 types of modified policy iteration, and we compare our method, the twice regularized version, to the robust planning algorithms, like for each of these types of algorithms. And we see that R2, the computing time is more similar to vanilla, whereas robust takes much longer time to converge because of the computational time of each iteration to solve the minimization. So it's much more expensive. So the take-home message of all of this is that R2 MPI is has a similar time complexity as vanilla MPI or vanilla planning. And now I'm getting into the deep formulation of it. So the question is, okay, so if it's scalable, scale it. So the intuition is quite simple. Since we have the R2 Bellman operator, we can use it to have an R2 TDR, temporal difference. So in temporal difference methods, what you do is that your loss function is defined as the gap between the Bellman update and the current estimate. So exactly the same here. So instead of having just R plus gamma max here, minus the current estimate, we add this regularization here, which accounts for the reward and transition uncertainty. Yes, so we can formally show that it converges to the optimal robust Q value. So in fact, indeed, you do recover the robust Q value in the end when you run this type of algorithm. And we can even extend it to an approximate method. We called it R2DDQN because instead of having here a tabular representation of a Q function, it's a neural network. And actually, there's one challenge here that I mentioned before is the estimation of the value. Here we have a dependence on the value function itself in the Q update. So how do we do that? The question. Yeah, how to compute this norm of V in a deep setting. You no longer have a tabular representation of it, so you cannot just take V to be the greedy Q function. Like you can relate the Q to V in a closed form formula, but in the tabular case, how would you do it? So to do that, we did whatever anyone does in a deep setting using a buffer. So you sample a batch of samples, sample a batch from BT from the replay buffer, and take an empirical norm of V. So you just feed forward your into the network and get an estimate of V according to that batch. And to have better stability. Also, we introduce a moving average that also accounts for previous estimates. And if we compare the different betas that we use in our moving average, so for example, if beta equals 1, you don't do a moving average at all. You just account for your current estimate. But if beta converges to 0, what we see is that, okay, so this beta equals 1 is the blue curve. So you see high variance, but quick convergence. And if you take beta very close to 0, you get very slow convergence, but on the other hand, the variance becomes slower. So you need to choose something in between. Yeah, so for example, I don't remember which one we used, but I think the yellow one was the best choice, actually, in practice. And we ran this on continuous environments such as Carpal, Acrobat, Mountain Car, which are correspond to continuous state spaces, but discrete and finite action spaces, actually very small action spaces. I think only 2 actions. And we see that if we do exactly the same as we did in planning, meaning comparing the time computation for each update, we have similar results as before, meaning that here the R2 updates take similar time as vanilla. So the similar take-home message here, R2 DDQN time complexity is similar to vanilla. These correspond to the convergence of the 3 baselines. So you can empirically see that at some point it converges. Vanilla is in blue, R2 is in red, and robust is in green. And what we did was to check effectively the robustness of each algorithm, meaning that after training, how robust is your policy? So once we converged, what we did was having like a shocking change of the parameters, physical parameters. So for example, this is in Mountain Car. If you drastically change the gravity, what happens to your reward during the episodes? And here the scaling corresponds to the reward the agent gets. So we can see here that the colors of R2 are similar to the robust ones, meaning that the performance of R2 is similar to the robust performance. So on the one hand, we have less computational time. On the other hand, we have similar robustness properties. And this is in a deep setting. So there's approximations, like there's some errors inside, but still we have the same observations in the end.
Do you have a plot where you only regularize the reward, but not for the...
No, I don't.
Okay.
That's a good question. Actually, it was not obvious how to introduce reward uncertainty in these environments. Because I think it was, maybe if it's stochastic, but yeah, we had a hard time to introduce uncertainty just in the reward and see what effect it has. But yeah, it would definitely be a good benchmark to compare to existing methods that only do policy regularization. So as like random ideas that come out from this research is the on the one hand, we have this reward regularization that takes the support in the reward. And on the other hand, we have this transition regularization that depends on the value. And if you think of the value as the infinite sum of discounted rewards, you see that on the one hand, you have like myopic regularization versus infinite horizon regularization. So maybe we can think of an intermediate way to regularize our operators. And I would define this as receding horizon regularization. Can we regularize, but only up to a certain horizon? And what kind of robustness properties this would lead to? And yes, so there's a whole bunch of literature on receding horizon reinforcement learning. So how to connect these two settings would be an interesting direction. So we ended up with a scalable robust RL with a theoretical grounding. Now the question is, can we do a robust policy gradient theorem as we did just for the reward robust setting? Can we generalize it to also transition uncertainty? And this is actually this year's EURIPS paper, where we focused on Boole uncertainty, and we can derive a robust policy gradient explicitly using regularization again. So following this theoretical work, we can now consider extending this robust approach to continuous control settings, such as like the question is, can you use algorithms like SAC or TD3 and robustify them by adding regularization in the policy updates? Yeah, so this is a bibliography, and if you have any question, I'd be happy to answer. Maybe I could have introduced the policy gradient work. I was scared of the timing.